So looking at this graph here, we can see that we have 8x over x squared plus 1. So first thing I notice is that there is a 0, so the numerator is equal to 0 and x equals 0. So I've kind of put that in my table, and I'm just going to plot that one coordinate. And I'm also going to do a limit here because I can see that this should be a horizontal asymptote at 0. So limit as x goes to positive infinity of f of x is equal to 0, and the limit as x goes to negative infinity of f of x, it tends to 0 as well. So I know I have a horizontal asymptote going through y equals 0. Okay, so I want to find some min and max points to graph this. So I'm going to find first of all, my first derivative. So f prime of x, when I differentiate this, I'm going to end up with, I'm just going to put the 8 on the other outside. So I'm going to end up with 1 times x squared plus 1 minus x times the derivative of x squared plus 1 is 2x. And I maybe should put those in square brackets on the outside here. And so that represents the derivative of the numerator of the derivative. And so I end up with x squared plus 1 all squared. I'm going to simplify that numerator. And so I end up with 8. This is going to end up being x squared plus 1 minus 2x squared. So I end up with so this ends up being 8. And I end up with 1 minus x squared in the numerator over x squared plus 1 all squared. Okay, so this is equal to 0. So f prime of x equals 0 at x equals, that's going to factor to plus minus 1. So at plus minus 1, I'm going to have a 0 slope. Okay, so there's my 0 slopes here. And then I should really test my slope. So f prime at negative 2 looks like I'm going to have at negative 2 when I plug it in, I'm going to end up with a negative slope. So again, I can look at the sign. So it's going to just, the new denominator is always positive. So I can just look at the sign of the numerator. So I'm going to end up with negative slope here. And then at 0, the slope is going to be positive. So it's going to be positive through here. And then at positive 2, again, I'm going to end up with a negative slope. So I know that it's going to go like that. So that's what my slopes are going to look like. And it's also going to hit an asymptote here. Okay, so there, I'm going to plug in my negative 1 and positive 1 to get a y coordinate. So as I plug in negative 1 and positive 1, so negative 1 into my f of x, I get negative 8 divided by 2. So it's going to give me negative 4. And I'm going to get positive 8 divided by 2. So that's positive 4. So graphing those two coordinates, I'm going to have, it looks like my min point here, and my max point is going to be here. Okay. So then so I've got my coordinates there, and I want my derivatives here. So my second derivative. So my second derivative, when I differentiate this now, okay, I'm going to keep that 8 outside again. So I end up with negative 2x times x squared plus 1 squared minus 1 minus x squared. And then that's going to be 2 times x squared plus 1 times 2x. Okay, you apply the chain rule through there. That's a pretty messy looking expression. Okay, so I need to be careful with my algebra through here. Okay, so expanding this out, I'm just going to zoom in here so I can see what I'm doing. So I end up with negative 2x. Expanding this out, I get x to the power 4 plus 2x squared plus 1 minus, okay, so this is going to be a difference of squares for, I'm just going to highlight it. These two terms are going to give me a difference of squares. I'm going to put the 4 on the outside here. I've got that extra x, and then the difference of square part, I'm going to end up with 1 minus x to the power 4. Okay. All over the denominator, x squared plus 1 squared. Okay, so simplifying this out still got a lot of work here to do, so I'm going to keep that 8 factored. I end with negative 2 x to the power 5 minus 4 x to the power 3 minus 2x minus 4x plus 4x to the power 5. Okay, I've got some like terms there. Okay, so I end up with 8. This becomes 2x to the power 5 minus 4x cubed minus 6x. Okay, I can factor that still, so I can simplify that further. There's a common factor of 2x, so that's going to come out on the outside. So I'm going to end up with 16x on the outside. And I end up with x4 minus 2x squared minus 3. And again, that's further factorable. That's essentially a quadratic pattern. So 16x, and that factors into x squared plus 1 x squared minus 3. Okay, so that factors into two numbers that multiply to negative 3, add to negative 2. And what ends up happening is we generate a factor that, and I made a mistake over here because this should be power 4. I need to square the denominator here, so that ends up being power 4. So we have some things canceling out here. So we end up with 16x, x squared minus 3. That's the numerator, which is going to give me my zeros for my inflection points. And I end up with x squared plus 1 to the power 3 now. So I don't need to worry about the denominator. And for that matter, the denominator is always positive. So when this is equal to 0, so when the second derivative is equal to 0, we know that x is equal to 0 and x is equal to plus minus square root 3. So putting that into my chart here, I've got it at 0. So I've got negative root 3. I want to find a coordinate for positive root 3. Those are going to be my inflection points. So negative root 3 and positive root 3 on my slope chart. I've got 0 inflection here, 0 inflection here, 0 inflection here. I should test my concavity, although I can kind of see what my concavity looks like. Okay, so f double prime at negative 2, plugging that into my derivative, my second derivative, I'm going to end up with negative in the numerator. So x squared minus 3 is positive times negative 2. So that's going to give me a negative. So I know that I have a negative concavity. Okay, so this is going to be negative concavity this way between negative root 3 and 0. I'm going to choose negative 1. When I plug that into there, I'm going to end up with x squared minus 3 is negative times negative 1. It's going to give me positive. So there's my positive concavity in here. And then doing the same for positive 1, I'm going to get negative concavity. and then my second derivative at positive 2, I'm going to end up with positive concavity here. It's going to look like that. Okay, and that kind of makes sense because this needs to be negative concavity because it looks like it's going to be curving towards that asymptote like that from the bottom, and same from the top. Okay, so I want to plug in a couple points here. Root 3, when I plug in root 3, I'm going to end up with, in the denominator, I get 4. I get 8 root 3 divided by 4, so I end up with 2 root 3. Okay, so that's going to be, negative 2 root 3. Okay, that's approximately 3.4, so negative root 3, somewhere around there, negative 2 root 3, maybe somewhere around here. Whoops, maybe somewhere a little bit higher there. Okay, so that's my inflection point. And I plug in root 3 into my expression. I'm going to get 8 root 3 over 4, so that's going to be positive 2 root 3. So this is symmetrical. So somewhere right about here, there's going to be my other inflection point. Okay, so I have all the points I need now, plus my slope chart. So sketching in this graph, my graph is going to have a horizontal asymptote, negative concavity, all the way to here. Then it's going to switch to positive concavity to get my max point. Go through the 0. It's going to change concavity. So it's going to be curving down through there. And then once it hits that red inflection point, again, it's going to inflect so that it can curve towards the asymptote in this way. So there's my graph. I've got lots of different things going on here. That second derivative is really, really messy. Okay, there's lots going on in here, so take your time and make sure you write steps down so that you don't lose track of anything so that you get inconsistent results.